All right, let's talk about what is, without a doubt, the most successful scientific theory we've ever come up with, the Standard Model of particle physics. I mean, think about it. It's basically the blueprint for our entire reality. It's the rulebook that governs pretty much everything. But you have to wonder, where did a rulebook this complex even come from?
What if this whole, incredibly complicated blueprint, with all its weird particles and forces,
What if it all just unfolded from one single beautifully simple idea? Well, that's what we're going to dig into today. The idea that our entire universe is built on a simple but really powerful concept, symmetry.
And look, I'm not just speaking metaphorically here. Physicists have discovered that if you start by demanding that the universe has a perfect kind of symmetry, the fundamental forces of nature aren't just a happy accident, they actually have to exist. The secret ingredient here is a concept called gauge invariance.
So, at its heart, gauge invariance is actually pretty intuitive. It just says that the basic laws of physics can't depend on your personal point of view. Imagine you and I are building a house from the same blueprint. If your idea of up is different from my idea of up, we're going to have a problem, right? We'd need some kind of universal reference, like a bubble level, to make sure we're all on the same page. Gauge invariance is basically the universe's version of that bubble level.
Okay, so check this out. This is where it gets really cool. What happens when you actually enforce this rule? You start with just one thing, a single electron. Then you make a demand. You say the laws of physics have to work perfectly, even if the way we measure the electron's properties changes from one spot to the next. The moment you do that, the math just breaks. The equations stop making any sense at all. The only way to fix it, the only way to make the math consistent again, is to invent a new field that connects every single point in space and acts as that universal reference. And here's the kicker. This field you were forced to invent, it turns out to be electromagnetism. And the particle it uses is the photon. A whole fundamental force of nature just pops into existence simply because you demanded symmetry. It's amazing.
Now, if you're thinking, that's a powerful idea, you are absolutely right. Because if demanding a simple symmetry just gives you electromagnetism for free, you got to ask the question, right? What happens if you demand even more complex symmetries? Well, turns out you get the rest of the standard model. Let's see how that works.
So here it is, the whole shebang. By applying different, more complicated types of symmetry, which we describe with these mathematical groups, you literally generate the other forces. The simplest one, U1, that gives us electromagnetism and the photon. A more complex one, SU2, gives us the weak nuclear force with its W and Z bosons. And an even more complex one, SU3, gives us the strong nuclear force and its gluons. The entire foundation of our physical world, all derived from one principle. It's almost perfect. Almost.
Because this absolutely beautiful, elegant theory, built on the idea of perfect symmetry, runs headfirst into a massive problem when you look at the real world. A huge crack appears right down the middle of this perfect blueprint. You see, the math here is completely unforgiving. If these underlying symmetries are truly perfect, like the theory demands, then all the particles that carry the forces, the photon, the gluons, the W and Z bosons, they all must have zero mass. Now for the photon and gluons, that's great, they are massless. But when it comes to the weak force, well, that's where the trouble starts. The theory just violently disagrees with reality. The theory screams that the W and Z bosons must be massless, but when we go out and measure them, they're absolute heavyweights. I mean, they're some of the most massive fundamental particles we've ever found. The theory and the facts were in a total head-on collision.
And this was a huge dilemma for physicists. How could this principle of symmetry, which worked so brilliantly to build the forces, be so completely and totally wrong about something as basic as mass? How can nature be built on this perfect idea, but then not actually follow the rules?
And the answer they came up with is it's one of the cleverest ideas in all of science. The idea was, what if the symmetry isn't actually gone? What if it's just hidden? This is the whole concept of spontaneous symmetry breaking, and you've probably heard of its most famous consequence, the Higgs field.
Spontaneous symmetry breaking is this wild idea that the rules of the game can be perfectly symmetric, but the outcome isn't. The laws of physics themselves can still hold that perfect symmetry, but the universe itself, the vacuum, the very stage everything happens on, can kind of choose a state that breaks it.
The classic analogy makes this so much clearer. Imagine you have a wine bottle with a big punt in the bottom. Now, if you put a little ball right on the center peak, its situation is perfectly symmetrical. But it's not stable. It's going to roll down into the valley, right? Now, that valley is also a perfect circle. It's totally symmetric. But for the ball to be in its lowest energy state, it has to settle at one specific point in that valley. By settling there, it has broken the perfect rotational symmetry. The rules were symmetric, but the final result is not.
And that is exactly what the Higgs mechanism proposes happened to our universe. As the very early universe cooled down, it settled into its lowest energy state, just like that ball rolling into the valley. In doing so, it broke a fundamental symmetry and filled all of space with the Higgs field. Now, particles like the photon don't really interact with this field, so they just zip right through, remaining massless. But other particles, like our W and Z bosons, really do interact with it. They feel a kind of resistance, a drag, as they try to move through it. And that resistance, that is what we perceive as mass.
So, with this incredibly ingenious patch, this idea of a hidden, broken symmetry, the Standard Model was finally complete. It wasn't just fixed, it was ready to face its ultimate test against cold, hard reality.
And let me tell you, the results from those tests have been nothing short of spectacular. This isn't just a nice story that ties everything together. This is a theory that makes predictions with an accuracy that is just, it's mind-boggling.
Take a look at this number. This describes a tiny magnetic property of a particle called a muon. It's one of the most precisely measured things in all of science. The Standard Model predicts what this number should be, and the prediction matches the measurement to an accuracy that's like measuring the distance from New York to Los Angeles and being off by less than the width of a single human hair. It's just insane.
Or how about this one? Physicists were wondering, how many different types or families of lightweight neutrinos are there? The Standard Model, just based on its own internal logic, made a very firm prediction. There have to be exactly 3. So they ran the experiments to measure it. And what did they find? 2.984, with a tiny margin of error. I mean, come on, that's a direct hit.
And for one last example, look at the mass of the Z boson. Using a bunch of other measurements, the model can predict exactly how heavy this particle should be. And as you can see on the chart, the prediction and the measurement are practically sitting on top of each other. Time after time after time, the theory just nails it.
So it's really no surprise that physicists talk about this theory in such glowing terms. This quote really sums it up perfectly. It is, without a doubt, one of the greatest intellectual achievements in human history.
So I think the real takeaway here is that the Standard Model isn't just some boring list of particles and forces. It's a profound story. It shows us that the incredibly complex and rich reality we see all around us can be derived from one simple, elegant, and deeply powerful idea: the demand for symmetry. But for all of its incredible success, we know this blueprint isn't the final story. It doesn't have a place for gravity, for one, and it can't tell us a thing about huge mysteries like dark matter. Which leaves us with the most exciting question of all. If symmetry was the key to unlocking this blueprint, what new, even deeper principles and what strange new particles are waiting for us to discover as we try to venture beyond it?